Okay, we're going to take a look at finding a number of different derivatives and using a number of different processes to do this. This will be, we're going to go through 8 examples. This will be a longer video, but we're going to go through power rule, product rule, quotient rule, chain rule, some combinations of those. Feel free to skip around through the video, but we're going to go through starting with our power rule, and our power rule says that when we're finding a derivative of a term that can be expressed like this, and I'm going to use this little prime symbol to denote in the process of finding the derivative. What we can do is leave the coefficient, in effect bring the exponent down to join the coefficient, leave the x, and reduce the exponent by 1. Then all of the 4 terms in this polynomial for number 1 can be expressed in that form, particularly if I think of maybe this term as negative 2x to the first, and sneaky kind of the 12 as plus 12x to the 0th. Okay. But one nice thing about derivatives is derivative processes are distributable over addition and subtraction. So when I'm finding the derivative of this quadrinomial, I'm in effect just finding 4 different simple little derivatives. So f prime x, and I'm going to take a step probably more than most of you would take doing this, just to illustrate our power rule, would be first term, I'm going to leave the 3, I'm going to bring the 4 down to join it, x to the, I'm going to reduce 4 by 1. Then as I kind of distribute the power rule through this, I get minus 5, bring the 2 down, leave the x, reduce 2 by 1. Minus 2, bring the 1 down, leave the x, reduce 1 by 1. And again, probably more steps than you would need, particularly maybe in this case right here on this part. Next, I'm going to go plus 12, bring the 0 down, x, reduce 0 by 1. So I end up with, for my derivative, 12 x to the third minus 10 x to the first minus 2 x to the 0th, but of course x to the 0th is 1, plus 12 times 0 times x to the negative first, but 12 times 0 is 0, 0 times 1 on x, 0. So there is our f prime x, or our derivative. Now, as we're doing this, there's a much easier way to arrive at this minus 2 as we're going through the process than to go through this whole thought process up here, making it 2x to the first, x to the 0th. We need to remember a derivative is just a slope formula. So I'm trying to find the slope of this guy, and I say, oh, I guess the slope of that guy's 12x cubed. Huh, I didn't know that. Then I'm trying to find the slope. I don't know what the slope of negative 5x squared is. I guess it's negative 10x. But once I get to that point, I'm left with a linear term, negative 2x plus 12. And I say, well, what is the slope of y equals negative 2x plus 12? If you're watching this video, you ought to know that the slope of this guy is just negative 2. So once we get down to a linear term, don't forget a derivative just finds us the slope. Now, the power rule will do some other things for us that you might not think at first. The power rule could find, for instance, the derivative of, let's say, 2 on x to the third, because we can think of that as 2x to the negative third. And the derivative of that would be bring the negative 3 down with the 2, negative 6 x to the reduce negative 3 by 1, negative 4, or negative 6 on x to the fourth. And we might not look at this and initially think, oh, the power rule works there. Likewise, we might not look at this guy, third root of x squared's derivative. Well, how in the world does the power rule apply to that? Well, because radicals can be written as exponents. This could be represented as x to the 2/3. And if we're finding that derivative, I bring the 2/3 down in front. I leave the x. I reduce 2/3 by 1, negative 1/3. And if we want it in radical form, that would, of course, be 2 over 3 times third root of x. So power rule, pretty handy. That's pretty much our go-to rule. So a couple of the others, there's a little bit more involved in them, but that's a really useful one for us. Okay, let's take a look at this guy. And in this case, I have a function of x times another function of x. And it'd be wonderful if we could just take the derivative of every little thing here. But we can't do that. When we have a function of x times a function of x, we have to use our product rule. And our product rule states that if I have some function of x times some function of x, then what I want is the derivative of the first function times the just plain second function plus the just plain first function times the derivative of the second function. So my first function in this case being, we'll consider this guy to be f. My second function, we'll consider this guy to be our g. My first function, secant. Well, that's one of those that we need to know, and the derivative of secant of x is given as secant of x times tangent of x. So my first function derivative is secant of x tangent of x. I need times my plain old second function, 5x cubed minus 3. Don't forget the parentheses, they matter. Plus my plain old first function, secant of x, times the derivative of the second, or the derivative of 5x cubed minus 3. So times 15x squared. And then we may consider from that point on moving into an algebra or a trig phase, see if we can simplify some of these things. And I'm going to leave that for the observer. But that gets us through the calculus portion. You'll often hear people say, calculus, really, really easy. The only problem with calculus is it turns into hard algebra and some trigonometry at times. Okay, so there is a basic product rule with a trig component. Okay, and now it would be wonderful looking at number 3 if we could just say, well, the derivative of 4x is 4, derivative of 6 is 0, this is 4x, this is minus 3, and just call this thing 4 on 4x minus 3. But we can't distribute the power rule or derivatives over a division sign. We have a quotient rule for that. And our quotient rule states that if I have a function of x on a function of x, and I'm looking for the derivative, that I take the plain old bottom function or denominator times the derivative of the top function, subtract that, or subtract from that the top function times the derivative of the bottom, and all of that goes over the bottom function squared. If only there were a nice little poem to remember that with. So instead of thinking of this as top function, bottom function, numerator, denominator, I am going to think of this guy as my high function. This is my low function, and anywhere I'm taking a derivative of one of those, I will call that either d high or d low. So as we track through this, this would be low, d high minus high d low over the square of the thing below. Low d high minus high d low over the square of the thing below. And every time I've done one of these problems in my life, I've recited that at least under my breath. Low d high minus high d low over the square of the thing below. So f prime x, or my derivative, is low 2x squared minus 3x minus 11. That is low. D high, derivative of the high function, just plain old 4. Low d high minus high 4x minus 6 times d low 4x minus 3. So where are we at now? I've got low d high minus high d low over the square of the thing below. And once again, calculus, pretty easy. Algebra, now I'd have to do some distribution, some foiling, distributed negative, superfoil the denominator, maybe see if I can combine terms, maybe ultimately see if I can get some common factors and reduce. It's almost like you graduate into calculus to a point where I can hire algebra people, but it's like a secret society in calculus where, you know what, the calculus works pretty easy. Let's just not explain it to all the algebra people, and we can hire them to do the tough stuff for us. Okay, well, I'm going to have to write pretty small on this guy. As I can see in this one, I have a division, which is quotient, but I also have a product in here. I'm going to have to use some quotient rule and product rule. It's important that I see, though, that in the big scheme of things, this is really a quotient. There just happens to be a product in it. And if you just watched example number 3 prior to this, you're aware that our process for this is we're going to go for quotient rule, low, d high minus high, d low over the square of thing below. So I need a low function, I need a high function, I've got those. I'm going to need a d low, derivative low function, what a breeze. But I'm going to need a d high function, and that's the biggest sticking point. So I'm going to organize this by just first finding my derivative of the high function. So derivative of high function, this is a product rule. And if you refer back to problem number 2, we go through the formula for product rule. I want to take the derivative of first, and the derivative of tangent is just one of those things we need to know. Derivative of tangent of x is secant squared of x every time. So that is derivative of first times the just plain second, 2x minus 4, plus the just plain first, tangent of x, times derivative of second. So that is my d high. I haven't started finding the derivative of f of x yet. I just found the derivative of the numerator, or my d high. That way, and again, if you need some review on that, you can go back to problem number 2 where we went through product rule. So now, quotient rule, I ought to be able to go with my low d high minus high, and d low is a breeze. Low d high minus high d low over the square of the thing below. Let's go. F prime x equals low d high. Now, just in the interest of space here, I'm going to say that my d high equals star. So I need low d high. So we're seeing all of this guy right here. Low d high minus my high function, tangent of x times 2x minus 4, low d high minus high d low. Well, d low is a breeze. D low, the derivative of 11, 11 is a constant. The derivative of a constant is 0. Derivative of negative 6x squared, negative 12x. Low d high minus high d low over the square of what's below, over the square of the thing below. So there it is. So that's the way you may want to partition this, is if you have a quotient rule problem, check and see. We need four things. We need a low, we need a high, we need a D low, we need a D high, and check and see, are any of those things going to cause problems? In this case, the low was a breeze, the high's a breeze, the D low's a breeze, but the D high got a little bit extra work to do, so I kind of segregated it and took care of it first. Okay, let's move on to number 5. Yikes. Let's go to that thought process we just went through right at the end of problem number 4. And let's take a look at this guy. This is clearly a quotient rule, but within the quotient rule, we have a quotient. So I'm going to go through that little check system. I know I need to have a high function. I know I need to have a low function. I know I need a D high. And I know I need a D low, derivative low. So the high function, it's not real pretty, but it's real simple. It's right there for us. High, simple. Low, simple. D high, yikes. Yikes. And D low, simple. So I think I'm going to organize this much like I did number 4. I'm going to start by just figuring out what D high is, because that is definitely our troublemaker. So here is D high. My derivative high, I'm talking about my derivative of this guy right here, 4x on 3x cubed minus 5. Not so bad when I don't look at 11 minus 6x. I get this guy up here above the line. I get its low, 3x cubed minus 5, low, D high, the derivative of the high is just 4, minus high, 4x, D low, oh, D low is not a problem. Now D low here is just 9x squared. The minus 5 constant cancels. So that is low, D high, minus high, D low, over the square of the thing below. And don't be confused by that. That is not our final answer. That's just D high. That's why this was a yikes. Okay, but now we can put the thing together. Now we can put the whole derivative together. F prime x is a quotient where my high function is 4x on 3x cubed minus 5. My low function is 11 minus 6x squared. I want low. 11 minus 6x squared. D high. Yikes. Star for the in the interest of space. Minus high. Well, it's not pretty, but it's not a problem either. So where am I now? I've got my low, D high, minus high, D low. Oh, D low's not a problem. D low, the derivative of the low function, negative 12x. All on the square of the thing below. And then, of course, we may have some pretty rough simplification here, but we will pass that on to a good sophomore algebra student. Okay, we will now take a look at number 6. All right, here we move into chain rule. So the chain rule states that if we have a function inside a function, and we are trying to find its derivative, a function embedded in another function of x, or we could decompose the functions, that we should end up with f prime g of x times g prime of x. What does that mean? Well, f prime of x, f would be our outside prime, our derivative. It's our outside derivative of our inside function, g of x being our inside function, times our inside g's derivative. So that's worth having written down. The outside derivative, so I'm going to write it pretty small here. We want the outside derivative of the inside function times the inside derivative. And maybe the most important word out of all this, we got some good sounding mathematical terminology, outside derivatives, inside functions, inside derivatives. But maybe this little preposition right here is as important as anything there. The outside derivative of the inside function, you'll see what I'm talking about, times the inside derivative. So off to the side, when you get good at chain rule, you probably don't need to do what I'm about to do, but I'm gonna decompose this function into an inside and an outside function. And clearly our inside function, I'm going to call it I, is 12x cubed minus 4x. And our outside function is x to the 8th. Well, I know I need to know my outside derivative along the way. So my outside derivative is 8x to the 7th. I know I need to know my inside derivative later on, so my inside derivative is 36x squared minus 4. So I've got all of my parts, so I think I'm ready to go. And I start with the outside derivative, and my outside derivative is a factory right here that wants to take things to the 7th power and multiply them by 8. But I am not finding the derivative of x to the 8th. I'm finding the derivative of this inside function. So my outside derivative wants to take things to the 7th power and multiply them by 8. But it is the outside derivative, here you go, of the inside function. The inside function being 12x cubed minus 4x. And if you stopped right there and thought about the power rule, you might say, well, that's what I expected the derivative to be all along. Just bring the 8 down in front, reduce the 8 by 1, and we've got it. But we're not done. What do we have so far? The outside derivative of the inside function, and now we need times the inside derivative. 36x squared minus 4. And there's all of our pieces, and that is a small chain. When we think of chains, we think of these interlocking loops, and this is a small chain. We're going to take a look shortly at a chain with an extra loop in it. Okay. Number 7. This is not a chain with additional loops, but it is still a chain rule. I have a rule for cosecant of x. And that's one of those rules, again, that you just need to know. The derivative of cosecant of x is negative cosecant x cotangent x. But I don't have a rule for cosecant of this mess. But this is an inside function, 6x squared minus 2x, with an outside function, cosecant x. Again, if you're really good at chain rule, you may not have to do this, but I'm going to go ahead and decompose this into my inside function, 6x squared minus 2x, my outside function, cosecant x. Therefore, my inside derivative, simple, 12x minus 2. My outside derivative, one of those things we need to know, negative cosecant x tangent x. Okay. So, as we learned back on problem number 6 prior to this one, the rule for the chain rule process, when we can decompose functions like this, is we want the outside derivative of the inside function. The outside derivative is the factory that takes things, puts them here and there. But I'm not putting x there because I'm not finding cosecant of x. I'm finding cosecant of that guy. That's the inside function. So I want the outside derivative, got it, of the inside function, 6x squared minus 2x, and 6x squared minus 2x. What do I have so far? The outside derivative of the inside function. But I'm not done yet. If you look back on slide 6, I still have to take that times the inside derivative, because chain rule says it is the outside derivative of the inside function times the inside derivative. One more time. It's the outside derivative of the inside function times the inside derivative. And here's our inside derivative, 12x minus 2. It's a beautiful thing. And let's take a look at one more. Here is our multiple chain. Okay, so as I'm trying to desegregate this into inside, or decompose this into inside-outside functions, I notice I could really say, well, I got a most inside function, then I've got kind of an intermediary function, and then I've got a most outside function. So how do I separate this just into insides and outsides? The way we want to do this is just like kind of like eating an artichoke. You just start peeling it away from the outside. I want to consider ln x as my outside function. And we have talked about in class that the derivative of ln of x is 1 on x. So my outside function being ln of something makes my outside derivative 1 on something. But 1 on what? I'm not finding the derivative of ln x. I'm finding the derivative of ln 3x squared minus 2x to the 10th. My inside function now is all of 3x squared minus 2x to the 10th. What have I found so far? My outside derivative, 1 on, of my inside function, including the exponent to the 10th. I still have to take that times my inside derivative, but I have peeled away ln, and I'm now finding the derivative of this guy, which is still a chain, but it's a chain now that's very, very clear to me. I've got an outside function, x to the 10th, an inside function, 3x squared minus 2x. So my outside derivative is 10 something to the 9th. 10 what to the 9th? I'm not finding x to the 10th's derivative. I'm finding 3x squared minus 2x to the 10th's derivative. So I want the outside derivative of its inside function, 3x squared minus 2x. But how do I find the derivative of this chain? I need the outside derivative of the inside function times the inside derivative. I still need to find this guy's derivative right here. That's the inside of my x to the 10th. So that guy's derivative, of course, is 3 times 2, 6x minus 2. And then we may have some cleaning up to do. In fact, this is so good, and this happens on ln derivatives quite a bit. You get this situation right here. This is too good to pass up. So numerator, I would have a 10 and a factor of 6x minus 2, but 9 of these guys that want to be in the numerator can wipe out 9 of those common factors in the denominator, and I end up just with 3x squared minus 2x to the first in the denominator. And that is probably worth some review along the way, but a lot of information there, and probably worth pausing, going back through that at some time.